Hello everyone, my name is Hafam. I'm a researcher from Halme University of Applied Sciences in Hämeenlinna, Finland. Today I'm presenting about RoboEval. It is an LLM powered chatbot framework for interactive evaluation of robotic systems. This paper was completed together with my colleagues Hong Bo Yang and Ariza Chuaman. As you can see from the right side, there are some key results. 35% reduction in evaluation time, an average user satisfaction 4.4/5, a significant result at p less than 0.001, and a study involving 20 participants. Okay, let me briefly outline what we will cover today. We begin with motivation, why current robotics evaluation methods are inadequate. Then we define 3 specific research gaps which RoboEval addresses. From there, we move into the system itself with architecture and prompt engineering strategy. In the second half, we cover evaluation methodology, including a study with 20 participants, an ablation analysis. We then look into the result, discuss limitation honestly, and we will close with the future direction and conclusion. Let's start with the problem. The robotic systems are now deployed across industrial automation, healthcare, logistics, and many other domains. As this deployment grows, complexity is required to have robust and reliable evaluation methods. But here is the challenge. The current evaluation method that we are using now have not kept pace. From the left side, you can see the hallmark of conventional evaluation, which is rigid, predefined benchmarks, simple success rate tallies. The method requires evaluator to have deep domain expertise. Those tools cannot adapt to specific context of what being evaluated. Also, it meets qualitative failure insight, which matter most in real-world deployments. Now, on the right side of the slide, consider a different paradigm. What if an evaluator could simply have a conversation? What if the evaluation system could ask follow-up questions, adapt based on what is here, extract both numbers and narrative insight, and deliver feedback automatically? This is the vision of evaluation as conversation. And the reason we can now attempt to build is immersion of large language model which support multi-tone dialogue and domain adaptation. To round our contribution, we conducted a systematic review of documents and identified 3 gaps. Gap number 1. There are no conversational evaluation tools. The existing robotics benchmark evaluate systems with predefined metrics. None of them provide an adaptive conversational interface that modify questions based on what evaluator reports. Gap number 2. Poor non-expert accessibility. Standard evaluation tools assume that the evaluator familiar with robust metrics. This excludes a large population of relevant end users, field operators, healthcare professionals, and others who are domain experts in their own field but not in robotic evaluation specifically. Gap number 3. No unified integration of qualitative and quantitative assessment. Current method force a choice. You either collect quantitative metrics, for example success rate, completion time, error counts, or you collect qualitative feedback through an open-ended questionnaire. There is no single framework that captures both in real time during a single interaction. RoboEval was designed specifically to close all 3 of these gaps simultaneously. To show where RoboEval sits in the existing landscape, we built this feature comparison table. It evaluates 6 approaches: benchmark suite, questionnaire, the Stanfield XRI taxonomy, LLM as choice method, conversational usability testing, and RoboEval across 6 dimensions. Looking at the table, you can see that no prior approaches achieve all 6 properties. Conversational usability testing comes closest in the term of dialogue design, but it does not extract quantitative metric and is not tailored for robotics. RoboEval is the only approach that achieves all 6 properties simultaneously. This is the combination that contributes its novelty, not any single feature in isolation. Now let's look at how RoboEval is built. The system has 4 main components shown left to right in this diagram. First, the browser UI, a simple web interface where the evaluator types their response in plain English. Second, the Flash backend. This is the brain of the system. It maintains session state, tracks which phase of the conversation, communicates with the LLM API, handles errors, and writes to the database. Third, the LLM core, specifically GPT-4, running at a temperature of 0.4. We chose this temperature to balance response creativity with output consistency. The LLM receives the full conversation history at every turn, which allows it to give contextual, appropriate follow-up questions. Last, the SQLite database, which logs every dialogue turn, extract metric value, session timestamp, and confidence flag. The formula at the bottom of the slide captures the core logic. The response at 20 is a function of the conversation history, the current user input, and the phase-specific system prompt PS. This is what enables adaptive questioning. By changing PS at each phase transition, we change the LLM goals and output format without changing the underlying model. How does RoboEval achieve domain-appropriate behavior without fine-tuning the models? The answer is a 3 technique prompt engineering strategy. Technique 1. Role and context injection. At the very start of every session, the system prompt defines RoboEval identity as a robotic evaluation specialist, which specifies its vocabulary, the scope of its question, and the format of its output. You can see a real example at the bottom. Technique 2. Few short examples. Every phase prompt includes 2 to 3 work dialogue examples drawn from our own development sessions. We show the model not just what to do, but how to do it, the depth of follow-up question to ask, the format of the extracted output. Our application study, which I will show shortly, found that removing the assembler dropped dialogue coherence score from 4.2 to 3.1. Technique 3. Structure output directive. When RoboEval needs to extract metrics, the prompt instructs it to return only the JSON block, no commentary. This single directive is the most critical component we identify. In our application study, removing it caused schematic parsing to fail in 67% of sessions. The combination of all 3 techniques is what produces reliable, domain-grounded, structure evaluation outputs. Let me show you how a real RoboEval evaluation workflow with a concrete example. The workflow has 4 phases. In the initiation phase, the evaluator describes the robot with its environment and the task being accessed. In the structure questioning phase, RoboEval begins asking targeted questions, and these questions adapted based on what was said before. In the analysis phase, responses are parsed to extract a hybrid evaluation profile. And in the feedback delivery phase, RoboEval produces a structural report with prioritized, actionable recommendation. The table at the bottom shows a real example from our case study on a robotic arm performing a pick-and-play task. The evaluator reports that 8 out of 10 attempts were successful. RoboEval immediately computes the success rate 0.8. It then continues asking whether specific object types were associated with failure. The evaluator mentioned creeper slippage on cylindrical object. The evaluator also gives the arm usability rating 4 out of 5, noting the creeper geometry needs refinement. RoboEval uses all of this to generate a targeted recommendation, optimize gripper geometry for cylindrical objects, and revisit the class planning parameters. For validation, we design a three-part evaluation strategy. The main component is a mixed method user study with 20 participants. Participants were recruited across 3 experience levels: 7 novice, 8 intermediates, and 5 experts in robotics. Each evaluated one of 3 robot platforms: a robotic arm, a mobile ground robot, or a quadrotor UAV. The study used a within-subject or counterbalance design, meaning every participant completed both RoboEval and the traditional questionnaire method. We collected Likert scale rating on 4 satisfaction dimensions with semi-structured follow-up questions and workload evaluation time for both methods. In response to viewer feedback, we added 2 further components. First, an expert baseline comparison. An independent domain expert with over 5 years of experience in robotic manipulation evaluated the same session as the case study, applied to RoboEval outputs. This provides a ground truth for assessing whether RoboEval extracted metrics are accurate. Second, a retrospective ablation study across 6 sessions, 2 per platform, testing 3 degraded prompt configurations. This lets us isolate which design choice actually drive performance. Now for the results, let me start with the headline number, a 35% reduction in evaluation time. RoboEval achieved a mean time to report of 7.8 minutes compared to 12 minutes for traditional questionnaire method. We ran paired t-tests to test statistical significance. The result is t of 19 equals 6.42, p less than 0.001 with a coherence d of 1.44. The 95% confidence interval on time difference is 2.6 to 3.4 minutes. Turning to the satisfaction results shown in the table, each of you scored Highgate at 4.6 out of 5 with a standard deviation of only 0.4. Feedback accuracy was 4.3, overall satisfaction 4.4, and dialogue coherence 4.2. All 4 dimensions carry confidence interval comfortably above 3.8. Suggesting robustness even with a small sample size. This slide presents the 2 deeper validation components. On the left, the expert baseline comparison. When we compare the domain expert evaluation against RoboEval outputs on the same robotic arm session, we see the following. Both arrive at exactly the same success rate of 0.8. Both identify the same primary failure mode, Reaper issue with cylindrical object expressed in slightly different words. Both gave usability rating of 4 out of 5. The expert report took 40 minutes. RoboEval produced its output in 8. However, RoboEval produced one additional claim that the expert did not make. This is a hallucination. I will discuss this more in the next slide, but the key point here is that RoboEval agrees exactly with the expert judgment. On the right, the ablation study, we tested 3 degraded configurations. Removing the round prompt dropped coherence from 4.2 to 3.8. Removing the few short exemplar dropped it further to 3.1. But removing the structure output directive had the most severe impact. Mean coherence dropped to 2.4 and metric parsing failed in 4 out of 6 sessions, a 67 failure rate. Now I would like to spend time on limitation, on hallucination. We documented 3 patterns in our study. The first is unsupported causal claim. The RoboEval linked a failure mode to a root cause that evaluator never described. This happened in the expert comparison we just saw. The second is metric interpolation, where the model infers a metric value that not directly elicited from the dialog. The third is inconsistent follow-up, where the chatbot re-asks a question the evaluator already answered, which occurred in approximately 15% of sessions. On study design, n equals 20 is a small pilot study. Our conclusion should be treated as preliminary evidence, not definitive findings. Platform assignments were balanced across experience level, but not fully randomized due to equipment access constraints. The ablation study were retrospective and involved only 6 sessions, and the most fundamental limitation, the current system relies entirely on evaluator supply description rather than the live sensor data. These are not the reason to dismiss the work, they are reason to continue it, and thus bring me to the future directions. We have 4 future directions. The highest priority is real-time sensor integration. This is the single chain that would most fundamentally improve RoboEval reliability. This addresses the core objectivity limitation we just discussed. Second, adaptive learning through reinforcement learning from human feedback. Over time, as RoboEval conduct more evaluation sessions, feedback from evaluators and experts could use to continuously improve the question selection strategy and the quality of its recommendation. Third, multimodal input, extending the interface to accept video clips and images, would allow evaluators to show RoboEval what they are describing, rather than relying entirely on text. For a large-scale randomized control validation study, we need N of 60 or more proper randomization across platform and experience level. Let me summarize the 4 contributions of this paper. Contribution 1. The RoboEval framework is one of the first structure phase-governed system for conversational robotic evaluation using large language model. Contribution 2. A fully reproducible design specification. We provide exact model version, the complete prompt templates for all 4 phases, the parsing logic, the database schema, and the error handling workflow. Contribution 3. A statistically crowded evaluation. This includes a paired t-test with a large effect size, 95% confidence interval on all satisfaction dimensions, an expert baseline comparison, and a prompt ablation study. Contribution 4. Honest documented limitation. We identify 3 hallucination patterns by name, disclose all study design constraints transparently, and describe the mitigation we apply. This kind of honesty is what makes a research contribute trustworthy and reproducible. To conclude, RoboEval demonstrates that evaluation as conversation is viable and practical paradigm for robotic assessment. We address 3 specific unmet gaps in literature simultaneously: the absence of conversational evaluation tool, poor non-expert accessibility, and the lack of unified qualitative and quantitative assessment. We achieve domain adaptation through prompt engineering alone, no costly fine-tuning required, and we show that the combination of raw injection, few short exemplar, and structural output directly produce reliable and reproducible results. The 35% reduction in evaluation time is statistically significant, p less than 0.01 with a large effect size. Expert comparison confirmed that quantitative metric extraction is accurate, and we have been transparent about the limitation, particularly around hallucination risk and study scale. Thank you very much for watching this presentation. If you have any question or would like to discuss about the work, please feel free to reach out by email. I look forward to engaging with community at the Colloquium. Thank you.